the uh, thank you, Mark, and other organizers for the invitation to give a talk in this seminar series. I'll be presenting my recent work, which was done in collaboration with Kamila Kowalska and Enrico Cecilo, where we extended their earlier work on a dynamical mechanism to generate small Yukawa coupling in the asymptotic safety framework. Particularly, we studied the feasibility of such a mechanism in two different models from the asymptotic safe gravity perspective. And we also investigated some of the gravitational wave signatures associated with this, with one of these models. So the outline of this talk, I'll briefly introduce the asymptotic safety framework, which most of you know quite well. And then I'll be talking about the dynamical mechanism that I just mentioned, how this comes about in this asymptotic safety framework. Then I'll be showing how viable is such a mechanism when we consider this asymptotically safe quantum gravity perspective. And then we will see the kind of predictions that we have for this new physics couplings in the extension of the standard model, and how these predictions vary based on different UV complete scenarios. Later, I will briefly review how we can compute gravitational wave spectrum for the predictions that we have. And then we'll see if it is possible to distinguish different UV complete scenarios with these kind of gravitational wave signatures. So we are interested in UV complete theory, which means that there are no couplings which diverge in the UV, and instead all of them approach a finite fixed point. So this means that such a theory can be extrapolated to arbitrarily large energy scales. And requiring such a consistency imposes a strong boundary conditions on these couplings in the UV. And we can see this by linearizing the flow of these couplings near the fixed point. Most of you are well aware of these concepts, but let me briefly recall them for the sake of completeness. Fixed point is where all the beta functions vanish simultaneously. And near this fixed point, we can define the stability matrix this way. And diagonalizing the stability matrix, we can find the critical exponents. Note that we are interested in finding out what are the free parameters in a given theory and what are the predictions in the theory. And this is determined by the critical exponents. For example, if a critical exponent is positive, then there is a range of values in the IR which would all match the flow from a UV fixed point down to high R. So this means the coupling associated with such a critical exponent is actually a free parameter of the theory. And this kind of flow is also referred as IR repulsive or even relevant couplings. And if a critical exponent is negative, then there is a unique trajectory between the fixed point value in the UV and down to a particular value in the IR. So this means these are the predictions of the theory, and they're also referred as irrelevant couplings. So there are many large N gauge theories which are actually UV complete and have a finite number of free parameters. And there is also a growing evidence suggesting that gravity could also be an asymptotically safe theory. As many of the people who have also spoke in this seminar series have shown this thing. So this means that if you consider Einstein-Hilbert effective action and apply this usual FRGE methods, we find that non-zero finite fixed point for the dimensionless counterparts of the Newton's constant and cosmological constant. And many people have also shown that this conclusion doesn't change much, even if we include different matter content to this analysis. So, but what we are more interested in is how such an asymptotically safe quantum gravity affects the matter sector. And we know that gravity effects can be parameterized in the leading order as shown here. And here, these are the beta functions of the gauge coupling, and this is for the Yukawa coupling. And this part is coming from the standard model physics and any new physics that we could have in the model. And Fg is the gravitational correction parameter, which depends on the fixed points in the gravitational sector. And Fy is correspondingly for the Yukawa couplings. Note that gravity does not distinguish the internal symmetries of the matter sector. So these kind of corrections are actually universal. What I mean by this is that Fg is same for all the gauge couplings, be it an SU3 gauge coupling or any new U1 gauge coupling. The value of Fg will be same for all of them. And similarly for Fy in the Yukawa sector. Note that there are large theoretical uncertainties in the computation of Fg and Fy due to different regulator choices or even gauge choices and the truncation schemes in the gravitational sector. So one way to go about this is to demand UV completion due to these gravitational corrections and see what values of this parameter fulfills such a condition and what are the consequences of it. So one possibility is where these kind of corrections could actually introduce on new interactive fixed points in the theory, and the couplings could be irrelevant, and this could lead to reduce the number of free parameters in the theory. For example, Astrid and Haron showed that it's possible to predict the mass of the top quark while ensuring the proper mass gap between the top quark and the bottom quark. These parameters are actually free parameters in the standard model alone, but this can be predicted in this kind of setup. Similarly, another possibility is where we can predict the value of any new physics couplings. For example, here, this is the beta function of the standard model hypercharge coupling, and this is for the new U1 gauge coupling. This model is quite similar to the model that I will also be discussing later. So for this theory, if we demand UV completion through an interactive fixed point for both of these coupling, then we can express the value of Fg in terms of the fixed point of Gy. And since we know the value of Gy in the IR, we can match the flow to determine this fixed point and correspondingly the value of Fg. And then we can also find the fixed point of this new gauge coupling. And once we know the boundary of this coupling, we can also find the value of this coupling in any interested IR scale. This way, it is possible to predict the value of new physics couplings. And another thing that I want to highlight is often the experimental searches for new physics constrain only the ratio of new physics coupling and the mass scale of some new physics with some higher dimensional operator, as I've shown here. And if we have a prediction for this kind of new physics couplings, then it's possible to estimate the mass scale of new physics as well, combining this with experimental constraints. Now we can ask how robust are these kind of predictions? Of course, discounting the theoretical uncertainties that I mentioned earlier. And since these couplings remain in the perturbative regime throughout the entire flow in this RGE flow, the predictions from this one loop beta functions are actually quite stable under higher loop corrections as well. And also note that the Newton's constant itself is scale dependent. So the value of the Planck scale is bit arbitrary up to few orders of magnitude. And also in this setup, we assume that the gravitational corrections decouple instantaneously below the Planck scale, which need not be the case, and this could be a smooth transition. In both of these cases, we want to see how these predictions change if we move this Planck scale by few orders of magnitude. And it has been shown that these predictions are quite stable under even this change of Planck scale. A more interesting scenario is these corrections could also help us address the problem of naturalness, at least some of the problems of naturalness that we would come across. For example, Wetterich and Yamada showed that it's possible to address the gauge hierarchy between electroweak scale and the Planck scale through what they call resurgence mechanism. And motivated by such a possibility to address the problem of naturalness, Enrico and Camilla proposed a dynamical way to generate a small Yukawa coupling in this kind of setup. So before I discuss the feasibility of such a mechanism in this gravity from the gravity perspective, let me quickly recap how this mechanism works and how that can lead to generate small neutrino masses. Note that there are two ways to explain tiny mass of the neutrino. And one way is where the Yukawa coupling of the neutrino is quite small. I mean, it should be 12 orders of magnitude smaller compared to the top quark Yukawa coupling. And in this case, after the spontaneous symmetry breaking, the neutrino acquires a Dirac-like mass term. This is similar to how other standard model particles acquire the mass. And another possibility is through seesaw mechanism, where the Yukawa coupling is still of order 1, but the observed neutrino mass is suppressed due to large Majorana-like mass term, which could be coming from some new physics, as we will see later. Note that in both of these mechanisms, the Yukawa coupling here is actually a free parameter. And we know that in the asymptotically safe, in the asymptotic safety framework, this need not be the case, and these could be predictions, as we will see in next few slides. Now we apply this analysis for the standard model with right-handed neutrinos. And these are the relevant beta functions while setting other couplings to their Gaussian fixed points. Here, this is the standard model hypercharge coupling, and these two are the Yukawa coupling of the top quark, and this is for the neutrino Yukawa coupling. And this also have the corresponding gravitational corrections, which are Fg and Fy, as shown here. Note that it is enough to restrict our analysis to just these three beta functions, because the value of other couplings remain very small for large part of this renormalization scale. So their effects is quite negligible, and our conclusions does not change much if we include them. So applying this kind of a fixed point analysis, we find two distinct scenarios based on the gravitational correction parameter Fy. Particularly, if Fy is above a certain critical value, then we have an IR attractive fixed point at a non-zero value for both neutrino and top quark Yukawa coupling, which is denoted here as D. Here, this means that both of these couplings have order 1 value at the Planck scale, and in this case, we still need a seesaw-like mechanism to explain the smallness of the neutrino mass. However, note that here the fixed point of this Yukawa coupling is irrelevant, and this is actually a prediction in this theory, and this means we can also estimate the scale of seesaw in this way. Now, the more interesting scenario is when Fy is below a critical value. In this case, we find an IR attractive fixed point at 0 for this neutrino-Yukawa coupling, which is denoted here as B. Here, the arrow points the flow from the UV to IR. So this means that if we have a UV complete scenario where the Yukawa coupling of the neutrino is of order 1 and top quark is almost 0, we would still flow down to this basin of attraction where the top quark will become of order 1 and the neutrino almost approaches 0. And few of these trajectories from the fixed point down to here are shown here in this plot in these blue curves. As you can see, it is possible to obtain an arbitrarily small value for this Yukawa coupling in this kind of setup based on different starting points in the UV. So this allows us to have an arbitrarily small Dirac mass for the neutrinos here. Now we can ask how viable is this kind of mechanism when we look from the perspective of the asymptotically safe gravity. So here, note that a crucial condition for this mechanism to work is an IR attractive fixed point at 0 for this neutrino-Yukawa coupling. And this means that the critical exponent of this Yukawa coupling should be negative. And doing some simple calculation from the beta function that I showed earlier, we find that this is only possible when the fixed point of the hypercharge coupling is also non-zero, which means that there is a one particular value for the gravitational correction parameter Fg, which can fulfill this condition. Because if it is a bit smaller, then Gy will have UV unsafe trajectories as shown here. And if Fg is a bit larger, then this would quickly pull the value of Gy after the Planck scale down to 0. And in which case, the critical exponent will still be positive and we will not have this mechanism working. So there is only a narrow range for the fixed points in the gravitational sector which could fulfill this condition. So now if we consider the calculation done by Astrid and others, we find that the fixed points in the gravitational sector should lie on this thin blue line if we want Fg to be this one particular value. And we also need to match the value of the top quark, and this imposes a constraint on the value of Fy as well, which is shown here in this shaded region. So note that in principle, there are computations for the Newton's for the fixed points of this Newton's constant and cosmological constant as well, which vary based on different gauge choices or regulator choices and truncation schemes. And if we consider one particular example or one particular computation by Donna and others, we find this fixed point to be somewhere over here. The main point that I want to highlight here is that there is only a small possibility for this mechanism to work in the standard model, since there is only a narrow parameter space for this fixed point to lie. So we redid this kind of analysis again for the B minus L model. Here, in the B minus L model, we have an additional U1 gauge group, which mixes kinetically with the standard model hypercharge. And we also charge the neutrino and few other particles under this new U1 group. So note that we have two new physics couplings in this setup, where G epsilon characterizes the kinetic mixing between the standard model U1 and the new U1 group that we have here. So here, it is still possible to have this mechanism working because we can still have this IR attractive fixed point at 0 for the Yukawa coupling, even if the fixed point of GY is 0. This can be seen by computing the critical exponent of this Yukawa coupling, which has, in essence, formed something like this. As you can see, even if the fixed point of GY is 0, it's still possible to have negative value for this critical exponent if the fixed point of this new gauge couplings is non-zero. So, and we also find the fixed point of this new gauge couplings.
Sorry, Abhishek.
Yes.
Your light turned off, so we can't see you. So if it's possible, sorry for the interruption, but we cannot see you anymore. Awesome, that's better now.
On the light, I'm sorry. Okay.
Thank you very much, and please excuse the interruption. Go ahead.
Okay. As I was saying, in this model, it is still possible to have a negative critical exponent if the fixed point of new gauge couplings is non-zero. And we also found that these fixed points are actually irrelevant for this gauge coupling, and these fixed point values can be determined by the value of Fg. And this means we also can find the value of these new gauge couplings in the high R as well. At least predict the value of this new gauge couplings. And since we have a larger range for the possible values of these new gauge couplings, there is a larger margin even for the Fg as well. So as I've shown here, based on the calculation that I showed earlier, all these different values for Fg can still fulfill this condition, and we could have this mechanism working there. And similarly, this dot shows the fixed point based on the computations of Donna and the others, which lies somewhere over here. So in essence, it shows that in the gauge B minus L model, it is much more feasible to have this mechanism working, since there is a larger range for this for the gravitational fixed point to lie, and it could be more viable in this gauge B minus L model compared to standard model with right-handed neutrinos. So for the rest of the talk, I'll be considering only this B minus L model. Now that we have a certain range for the value of Fg and Fy, we can see what are the possible choices for the fixed point and how observations constrain these choices. So particularly, I will consider this choice in terms of the fixed point of Gx and G epsilon as shown here. And we impose the following conditions on the choice of this fixed point. So first one, of course, we want to have this dynamical mechanism working in this model. That is, we need to have an irrelevant fixed point at 0 for this neutrino-Yukawa coupling. So this excludes the region where the critical exponent is positive, which is shaded in this gray region in this plot. And similarly, we also want to match the observed value of the hypercharge coupling. So this excludes the value of Fg below this particular value, which is shown, which is shaded in this green. And similarly, we also want to match the observed top quark mass. So this excludes some of the parameter space, which leads to a different top quark mass, and this is shaded here in brown. Here, this leaves out a small white region, which fulfills all of these conditions. And here I have shown for two different values of Fy. And here, these are the benchmark points that I have chosen. In addition to these, I consider two more benchmark points based on different values of Fg and Fy. And here I have shown the value of the new physics couplings, fixed points of these new physics couplings, and correspondingly the predictions of these couplings in three different scales. Note that the Yn here is actually a new Yukawa coupling, which mixes the right-handed neutrinos with a new scalar field, which is also charged under this new U1 group. And once this scalar field acquires a wave, this generates a Majorana-like mass term for the neutrinos. So if we consider benchmark point 3 and 4, we find that the fixed point for the Yukawa coupling is 0, and it's also irrelevant, similar to the neutrino-Yukawa coupling that I showed earlier. So this means that we can have the value of this coupling remain at 0 all the way from UV to IR as predicted here. So this means that RG flow ensures the 0 value for this new Yukawa coupling, and we have no Majorana-like mass term from this one. So this leads to Dirac-like neutrinos for these two benchmark points, these two UV complete scenarios. And in benchmark point 1 and 2, we have non-zero fixed point for this Yukawa coupling, and correspondingly, we have non-zero value predictions for this coupling in the IR. It will be later clear why I am chosen three different IR scales to note down the predictions. And in this one, since we have a non-zero value, here we have a Majorana-like mass for the neutrinos for benchmark point 1 and 2. Note that we also have...
Sorry, Abhishek,
Yes.
there is a raised hand by Aaron.
Yeah, I have a quick question, and that's concerning the new gauge couplings, Gx and G epsilon. In the UV, do you demand that they come from the interacting from an interacting fixed point, or do you allow also that they come from asymptotic freedom?
No, for these choices here, we have demanded that this comes from interactive fixed points. So both of these are irrelevant here.
And do you know whether this? So I think it's very interesting that you find that there's a kind of an FRG mechanism or an RG mechanism that drives the new Yukawa coupling to zero, or keeps it at zero. The YN. Do you know that that is correct even if you also come from the free fixed point?
If we come from free fixed point, in which case this both all gy, gx, and g epsilon all become zero for much of the RG flow.
Yes.
Also near the fixed point, in which case this critical exponent will not be negative. So
it reinforces the mechanism, right?
Sorry, I didn't hear you.
So this means that it reinforces that the new Yukawa coupling also must go to zero, even if you come from asymptotic freedom. I think.
The beta functions for this new Yukawa coupling are not shown here, but I think if the fixed point for this Jx and J epsilon also becomes zero, then we will have relevant fixed point for this Yn as well.
Can you say again, relevant or irrelevant?
Relevant. So
okay, yeah. Then the answer is that I think it's not. It's this Yn equals zero is only ensured if you come from the interacting fixed point.
Yes,
okay.
Only from the interacting fixed point. Yes. So, as I was saying, in all of these benchmark points, we also have prediction for this new gauge couplings Gx and J epsilon. And since we charge some of the particles under this new U1 gauge as well, and we also have kinetic mixing, this allows us to recast some of the experimental searches to put a lower bound on the mass of Z prime. And this bounds can be translated into a lower bound on the vacuum expectation value of this new scalar field, which is of about 10 TeV. Now that we have different predictions based on different UV complete scenarios, we can ask if there are any possible signatures, and if there are any, and if the signatures can distinguish between different UV complete scenarios. And since there is a new scalar sector which is spontaneously broken, one possibility is to have first order phase transition, which could lead to gravitational waves. So, in next couple of slides, I will briefly review how the predictions that we have can, using those predictions, we can have gravitational wave signals and how that comes about. So, to know the kind of phase transition that we have and the gravitational wave signals, we need to understand the scalar field. And since the wave of this new scalar field is much larger compared to the standard model X field wave, we can effectively decouple the X field from this kind of analysis. Here, this is the effective potential, which includes the Coleman-Weinberg potential, and this one is from the thermal potential. The Coleman-Weinberg potential includes our tree-level potential and also the contribution coming from the quantum fluctuations of the field. Here, this is the contribution coming from the gauge field, and this is from the fermionic-like fields. And note that the contribution from the fermionic fields is in the opposite direction compared to the scalar or the gauge fields. And this is the thermal potential, which depends on the mass term, which are dependent on the new physics couplings that we predict in this asymptotic safety framework. So in essence, we see that the new physics, the couplings that we predicted, determine how deep is the potential, and how deep is the potential in the true vacuum, and what's the height of the barrier, and how these parameters evolve with in a given in the thermal bath. And once we know the effective potential, we can use some of the standard machinery to calculate the gravitational wave amplitude. So note that the scalar field cannot smoothly roll over from the false vacua to true vacuum, since there is a barrier between them. Instead, a true vacua vacuum forms as a bubble at random points in the space and time through quantum tunneling or even thermal fluctuations. And then these bubbles start expanding and eventually collide with each other, breaking the spherical symmetry. And this could give rise to gravitational wave signals, which can carry the latent heat released in this process. So, as I said, the bubble nucleation rate depends on the kind of depth of the potential that we have, the depth of this effective potential, and the barrier between the vacua. And the strength of the signal also depends on the amount of latent heat released in this process, and the bubble nucleation speed compared to the universe expansion rate, and also the reheating temperature at the end of the phase transition. So in effect, the amplitude of the gravitational wave can be expressed as shown here. And this amplitude as a characteristic feature as shown in this plot here, with a peak of the amplitude in one particular frequency. Now that we have these methodologies, we can try to see if we have gravitational wave signals. And particularly, first, we will consider the well-known scenario of this classical scale invariance, where this mass parameter in the Coleman-Weinberg tree, this part is set to 0. Here, this model is well studied, and there is a direct correspondence between the gauge coupling, and the temperature at which the phase transition completes, which is characterized by this percolation temperature Tp. And here, as you can see, when the gauge coupling is below this critical value 0.25, then the percolation temperature is much below this QCD phase transition of 100 MeV. So in this scenario, we will not have gravitational waves that we are expecting. And this is the case for benchmark point 3 and 4, where the value of this gauge coupling is much smaller compared to 0.25, and we don't see any signal. And even in the benchmark point 1 and 2, where the value of this coupling is larger than this limit, even in this scenario, we still don't find the gravitational wave signal, because here in this analysis, they did not consider the Yukawa coupling, which is also quite large in our predictions. So including the effects of this coupling shows that the percolation temperature is still below QCD phase transition, and we do not have any gravitational wave signals, even in this case. And since we don't see any gravitational wave signal in this classical scale invariant case, we can ask if it is a justified assumption to assume this kind of classical scale invariant from the quantum gravity perspective. And similar to the gauge and Yukawa coupling, the gravity alters the flow of this mass parameter and the quartic coupling as well above the Planck scale. And these corrections can be parameterized as f lambda. And if f lambda is below minus much smaller than this -2, then we find an IR attractive fixed point at 0 for this mass parameter as well. So this means that here we have true quantum scale invariance. However, in this scenario, the quartic coupling actually goes to negative as we flow from UV to IR, and this destabilizes the vacuum. And even if we consider f lambda between -2 and 0, this does not change the conclusion much. So when we consider f lambda greater than 0, we find a relevant fixed point for both quartic coupling and the mass parameter. So this means that we can, this becomes the free parameters in the theory, and it's not completely justified to assume that even this mass parameter to be 0 in our analysis. On a side note, note that some of the FRG based calculations do suggest that f lambda is negative, but including some higher dimensional operators and other curvature terms could alter this conclusion. So, it makes more sense, or it's not justified to assume this mass parameter to set to 0. So instead, we assume the mass parameter to be a non-zero value, and we redid the computations of the gravitational wave. And in this case, we did find the observable gravitational wave signals. And this is because when we set a small non-zero value for this mass parameter, it actually reduces the supercooling, and it also lowers the thermal barrier. And this can lead to this kind of observable gravitational wave signals. Here in this plot, the y-axis shows the amplitude of the gravitational wave in the log scale with respect to the frequency that it's going to be observed. And the dotted line here are the projected sensitivities of future gravitational wave observations. And the solid lines are actually the computed gravitational wave spectrum for different values of the vacuum expectation value of the scalar wave, which is actually a free parameter in our theory. And as you can see, this spectrum is well within the sensitivity of these future observations, and the peak of this amplitude moves to higher and higher frequencies as we increase the wave. Now that we have an observable signal, we can ask if it is possible to discriminate the different UV complete scenarios that we saw earlier, whether we can see whether it is a Dirac-like case or Majorana-like case, if it is possible to distinguish through these kind of signals. As you can see here, for a given mass parameter, the amplitude of this gravitational wave signal is pretty much similar for all the benchmark points that we considered earlier. And also note that mass parameter is actually a free parameter in our theory. So if we increase this mass parameter value by few orders of magnitude, it suppresses the signal by several orders of magnitude. So in essence, we see that all the discriminating features are washed out due to the strong dependency on this relevant mass parameter. So to conclude, we saw that asymptotically safe gravity could induce an IR attractive fixed point at 0 for this Yukawa coupling. And this can lead to a dynamical mechanism to generate arbitrarily small value for this Yukawa coupling. And we also, I also showed that R-L model compared to the standard model with right-handed neutrino when we consider the perspective of quantum gravity. And since there is a new scalar sector in this gauge B-L model, this could potentially give rise to first-order phase transition that could lead to an observable gravitational wave signal, as I showed earlier. However, the discriminating features that we wished for through this gravitational wave spectrum are washed out due to a strong dependency on the relevant parameters. So with that, thank you. Thank you for your attention.
Thank you very much, Abhishek, for the nice talk. And we do have time for some questions. So if you have a question, please either raise your virtual hand or also your physical hand. And actually,